Hello, today we are stepping up our game, solving the coin flip problem. Previously, we've been stealing contracts in broad daylight, and now we have a harder problem where we are hacking a lottery. So we can start with checking what's going on here, and the instruction says that we need to build up our win streak, so guess the coin flip outcome multiple times. It wants to guess it 10 times in a row. So there's a really low probability of doing it manually. So we'll need to find a way of hacking it, a way of predicting the outcome. So now moving to the source code, we see that it's a regular coin flip, inherits nothing, uses safe math because it's an older Solidity version. It has some variables here, which are consecutive wins. So it must be a counter, which counts our wins. It has last hash, so we will see what's that. It can be a hash of anything at this point. And we have a factor. So it's probably something that you wouldn't want others to see. You wouldn't want to leak this RNG factor information. But we will see later how it's used in the smart contract. Then when the function is deployed, it invokes the constructor, which sets consecutive wins to 0. 0 is what we start with. It could be equals 0 here, but whatever. And then we have only one public function, which returns whether you guessed, whether you won or not. And let's see the logic. So starting from inner members, we get the current block number, and it's a public information. And we subtract 1 for whatever reason. Then we hash the block number and cast it to unsigned integer. So we'll use this block value. I think that as a pseudo-random number, in like other pseudo-random number generations, where you use time in your computer or whatever else, something that changes often. Then we compare last hash to block value, and if last hash equals block value, then we revert the transaction. So we also set last hash to block value. So okay, it means that we take the unit value of hash of the current block number -1, rather complicated thing, and then we say that we can trigger the flip function only once per given block. So if the block number changes, the last hash will equal block value, and the transaction will revert. And each block on Rinky I think lasts for like 12 seconds. So you can trigger the function once every, let's say 12, 13, whatever seconds. So then when we satisfy the one transaction per block condition, we go next to coin flip. It's an integer that takes the block value, so the strange pseudo-random number, and it divides it by factor. And then if the rounded number equals 1, it returns true. If not, it returns false. So we have this operator here for that. And because of the hash, and when a number is hashed, it has a given length, and the length stays the same, it makes it so that when you divide the number, there is a possibility that it's equal approximately it equals 1. So then when the side is equal to the Boolean value of what we pass, then we win, and we have consecutive wins counter +1. And if we lose, it defaults to 0, so you have to start again. So it's virtually not possible to solve this manually using your own luck. So we'll have to find a solution for that. And to do that, we'll need to somehow duplicate the RNG mechanism. So for sure we'll have to use a second smart contract. So we won't be invoking this contract directly. We'll use a second one to calculate something, to generate the number for us, and then send it to the victim, to coin flip thing. So for that, we need to start with getting address of the current instance. We haven't created a new instance, so the contract is not deployed yet. So now we are deploying it. And yeah, indeed, we have the instance address. We can copy it. And then we can move to our IDE of choice. We use Remix for simplicity. And here we start with having an ABI of the victim. So we basically took the whole interface. We provide any name we want, but we have the same interface of the only flip function, because we want to call the contract we have in our game, but we don't want to copy the whole thing here. We don't care about the implementation, we just want the ABI to be able to call it. And then we have our attack contract, which basically copies most of the implementation of the said lottery contract. So we have the factor, we have all of the block value stuff. We generate it the same way. We allow only one transaction per block. And we finish here when we have the side. And if you compare it to this code, when it has the side, it compares it to the guess. But if we generate the pseudo-random number the same way, we can pass it to this instance, and it will always equal true, because it will be the same block number, and the only variable here is the set block number, which changes every 12 seconds, so we have plenty of time to be right. Yeah, then we generate the side the same way, so we always have the same coin flip value, and we send it to victim, creating a new instance of victim contract above, and providing the victim address here in the parameter. We don't have to provide the guess, because we don't guess anything. We just hack the contract and we generate the same exact number every time, even if we send 100 transactions. So yeah, now we can go to the practical part and deploy it and see if it works.
Okay, so let's start with deployment of the attack contract. Let's set it. And also before, yes, check to inject that Web3 because we want it to have through the network. All right, let's wait a little. First, we want to show you that you can attack it directly from the remix. So we'll call the function attack once. Okay, let's go to the contract. And here we have to pass the address we want to attack. So it's the address from the Ethernaut. Yes, this one. And now we can attack. All right. Now, if we have the confirmation, let's check if the consecutive wins have been changed. Consecutive wins. All right. Okay, as we can see that there's a 1. Okay, so before we had 0, now we have 1, so once it's successful, but we need to do that 10 times because that's the main mission to complete while doing this coin flip task. But we don't want to uh, get the transaction to call the transaction 10 times waiting for it. So we'll go to Open Zeppelin Defender tool, and directly from there, we can show you how to make auto tasking. Okay, so let's add the contract. Let's leave it a name as attack, lottery attack, something like that. It's in the Rinkaby because we are using a Rinkaby network, and the address of the contract. All right. Also, it's verified because we verified it using Solidity Remix. Now we can add. And now we have the lottery instance. So our next step is to create the relay because we need the address to make auto tasks. So let's go to the relay sections and let's add the relayer. We can call it as just as we want. Okay, lottery relay network from the Rinky and we now we'll see some of the most important datas when it will be confirmed. So it's the address, it's API key, secret key. So it's worth to save that somewhere in the notes because it might be useful in the future. But we'll confirm that I written down the secret key and we can finish creating relay. Okay, so as we can see, we have no balance. So to change it, we'll just go to our MetaMask wallet and send some of if. Well, let's go for the send and just copy paste that address 0.05. Okay, great. And just send it. We could use faucet, of course, but it's the faster way for now. If you don't know how to get money on your wallet, we'll leave in description the link to the faucet where you can directly access addition of funds. Let's check if we have the money. All right. So now if we got the relay ready to making auto tasks, let's go to the auto task. Okay, let's add the first auto task. The name, it will be lottery attack, auto attack. Okay, great. We'll schedule this because we are not using webhooks. And the minimum amount has to be 1 minute. We cannot do it lower. Okay, now we'll choose the layer we'll be using. So just the one we just created. And we have to create some kind of Web3 connection to call the function. But we have it already. You can access it here. Let's scroll it down a little if you want to write it down. All right, and we can call the create because it will be creating the action.
Yes, after we change the addresses.
All right, because we've created new one. It was for the previous one because we've tried it before.
So our attack contract and victim.
Okay, let's create instance. All right, and now we'll be waiting for the 10 transactions to be confirmed. So we can just leave it at that, and we'll come back to you in 10 minutes. Okay, and that's just right. That's completed. So we hacked that, and we've managed to guess 10 times in a row the same thing as the current main source.
As you can see, after finishing this level, the Ethernaut game printed out some interesting information, and it's good to read it because we can actually realize that randomness in Solidity code basically doesn't exist, and whether you use Ketak or whatever else, it won't be truly random. But if you want to have like proven random numbers, you can either buy your own quantum random number generator, or you can use an oracle, for example, as suggested, very popular, Chainlink VRF. If you use any Solidity project templates, usually it's implemented in the template and very easy to use. And then you get proven random numbers that you can't easily hack, like in the example we just submitted. So that's it in this episode, and thank you for watching. See you in the next one.